It happened in complete silence. No explosion, no warning sirens, just a machine falling faster than anything built by human hands had ever fallen before. It crossed invisible boundaries that no spacecraft was ever designed to survive. Its temperature climbed, its antennas kept transmitting. Then, piece by piece, it disappeared. Not because engineers lost control, because they planned it that way. But the final minutes did something nobody expected. The last signals raised questions that scientists are still discussing years later. Stay with me, because this is the real story of what Cassini's final seconds actually revealed. On September 15, 2017, at precisely 10:55 UTC, mission controllers at NASA's Jet Propulsion Laboratory in Pasadena, California, watched a stream of radio data arriving from nearly 1.5 billion kilometers away. Those signals had already spent approximately 83 minutes traveling across the solar system. By the time engineers received them, Cassini no longer existed. The spacecraft had already plunged deep into Saturn's atmosphere, broken apart under immense pressure, and vaporized into glowing fragments long before anyone on Earth knew its mission had ended. It was the conclusion of one of the most successful planetary missions ever attempted. Yet for many scientists, those last moments were not simply an ending. They became the beginning of a new mystery. To understand why those final seconds mattered, we have to go back more than 2 decades. Back before Saturn had ever been explored in detail. Back before scientists realized just how strange its moons truly were. Back before anyone suspected an ocean capable of supporting life might exist hundreds of millions of miles from the Sun. The Cassini-Huygens mission officially began on October 15, 1997, when a Titan I-4B Centaur rocket lifted off from Cape Canaveral Air Force Station in Florida. It carried 2 spacecraft, NASA's Cassini orbiter, and the European Space Agency's Huygens probe. Together, they represented one of the most ambitious international collaborations in the history of planetary science. Their destination was Saturn, a planet nearly 10 times wider than Earth, surrounded by thousands of rings, accompanied by more than 100 confirmed moons, separated from Earth by distances that changed constantly as both planets moved around the Sun. At launch, Saturn was over 1.2 billion kilometers away. Getting there wasn't simple. There was no rocket powerful enough to fly directly. Instead, engineers designed a complex route involving multiple gravity assists. Cassini first flew past Venus, then Venus again, next Earth, finally Jupiter. Each encounter borrowed a tiny amount of orbital energy. Tiny by planetary standards, massive by human standards. Those gravitational boosts accelerated the spacecraft until it finally reached Saturn almost 7 years later. On July 1, 2004, Cassini fired its main engine for 96 minutes. If that burn had failed, the spacecraft would have sailed past Saturn forever. Instead, it slowed just enough. Saturn captured it. Humanity officially entered orbit around the ringed planet. Everything changed. The original mission was supposed to last only 4 years. Scientists hoped to study Saturn's atmosphere, its magnetic field, its rings, its largest moons. No one imagined the discoveries would justify extending the mission again, and again, and again. In the end, Cassini operated for nearly 13 years at Saturn, almost 20 years after launch, a remarkable engineering achievement, especially considering the harsh radiation, extreme temperatures, and immense distances involved. During those years, Cassini fundamentally changed humanity's understanding of the outer solar system. It photographed gigantic storms stretching thousands of kilometers across Saturn. It watched seasons change on a planet where a single year lasts almost 30 Earth years. It mapped the rings with unprecedented precision. It measured magnetic fields, sampled charged particles, observed lightning, tracked atmospheric chemistry, and constantly sent home images unlike anything ever seen before. By the mission's conclusion, Cassini had transmitted more than 635 gigabytes of scientific data, over 45,000 photographs. Thousands of scientific papers would eventually rely on those observations. Yet one discovery overshadowed almost everything else. It came from a moon barely 500 kilometers wide, a frozen world named Enceladus. At first glance, Enceladus appeared ordinary, bright, icy, cold beyond imagination. Surface temperatures could fall below minus 200 degrees Celsius. Nothing about it suggested activity. Nothing hinted at hidden oceans. Nothing implied biological potential. Then Cassini flew closer. On February 17, 2005, high-resolution images revealed long fractures crossing the moon's south pole. Scientists nicknamed them tiger stripes. The cracks appeared unusually smooth, geologically young, far younger than surrounding terrain. Something had reshaped this frozen landscape recently. The question was, what? The answer emerged unexpectedly. Later in 2005, Cassini detected enormous plumes erupting directly from those fractures. Water vapor, ice particles, organic molecules, all blasting hundreds of kilometers into space. Nobody had predicted this. Small icy moons were supposed to be dead, frozen solid, inactive for billions of years. Enceladus refused to follow the rules. Instead, it behaved like an active world. Cassini flew directly through those plumes. Its instruments sampled the material itself, not remotely, directly. The spacecraft identified water, carbon dioxide, methane, ammonia, simple organic compounds, tiny silica particles. hydrogen gas. Each new measurement added another layer to an increasingly astonishing picture. Beneath Enceladus's icy crust, there appeared to be a global liquid ocean, one kept warm by tidal forces generated through Saturn's immense gravity, an ocean hidden beneath kilometers of ice, an ocean venting material directly into space, an ocean that scientists could sample. Without drilling, without landing, without touching the surface, it sounded almost impossible. Yet the evidence kept growing. Then came another surprise. In 2017, shortly before the mission ended, researchers analyzing Cassini's data announced the detection of molecular hydrogen within the plumes. That mattered enormously. On Earth, hydrothermal vents located deep beneath our oceans release hydrogen through interactions between seawater and hot rock. Microorganisms use that hydrogen as an energy source. Life does not require sunlight there, only chemistry. Cassini had found evidence suggesting remarkably similar chemical processes could exist beneath Enceladus's frozen shell. Nobody claimed life had been discovered. That would have been scientifically irresponsible. But researchers could now say something almost as extraordinary. Enceladus possessed multiple ingredients considered essential for life as we understand it. Liquid water, organic chemistry, an energy source. 3 requirements, 1 tiny moon. The implications reached far beyond Saturn. Suddenly, the search for extraterrestrial life looked different. For decades, Mars had dominated that conversation. Now an icy moon nearly 10 times farther from the sun had entered the discussion, not because of speculation, because of measurements, because of evidence, because one spacecraft happened to fly through a plume of water erupting from another world. And Enceladus was only one chapter in Cassini's story. Its largest discoveries were still unfolding. Titan, Saturn's largest moon, had fascinated scientists long before Cassini ever arrived. It was larger than the planet Mercury, wrapped in a thick orange atmosphere, completely hiding its surface. For decades, nobody knew what lay beneath those clouds. Some imagined oceans, others predicted endless deserts of frozen hydrocarbons. The truth turned out to be stranger than almost anyone expected. On January 14, 2005, only months after Cassini entered Saturn's orbit, the European-built Huygens probe separated from the orbiter and descended through Titan's atmosphere. It became the first, and still the only, spacecraft ever to land in the outer solar system. For more than 2 hours, Huygens drifted downward beneath a parachute. Its cameras slowly pierced the orange haze. The images stunned mission scientists. Instead of a featureless frozen wasteland, Titan displayed branching channels, dark plains, rounded pebbles, drainage systems that looked eerily similar to river valleys on Earth. But these rivers had never carried water. At Titan's surface temperature of nearly minus 179 degrees Celsius, water behaves like solid rock. Instead, the rivers carried liquid methane and ethane. An entire weather system existed there. Clouds formed, rain fell, rivers flowed, lakes filled, not with water, with hydrocarbons. Titan had become the only world besides Earth known to possess stable liquids on its surface. Meanwhile, Cassini continued circling Saturn, completing flyby after flyby. Each orbit revealed another surprise. Each close encounter generated another question. The spacecraft studied Saturn's atmosphere in remarkable detail. Towering storms larger than Earth, jet streams reaching astonishing speeds, electrical lightning flashes thousands of times more powerful than those on our planet. One storm, observed in 2010 and 2011, wrapped around Saturn until it collided with itself. The storm system stretched for hundreds of thousands of kilometers. Nothing remotely comparable exists on Earth. Then there were the rings. From Earth, Saturn's rings appear smooth, elegant, almost delicate. Cassini discovered something entirely different. The rings were astonishingly dynamic. Tiny moonlets carved invisible paths through them. Gravitational waves rippled across billions of ice particles. Temporary structures appeared and disappeared. Propeller-shaped disturbances hinted at unseen objects buried within the rings. Every orbit revealed movement. Nothing was truly still. Scientists realized Saturn's ring system behaved less like a static disk, and more like an active ecosystem governed by gravity. Yet as the years passed, another reality slowly became impossible to ignore. Cassini was running out of fuel, not propulsion fuel, reaction control fuel. The spacecraft relied on small thrusters powered by hydrazine to maintain its orientation. Without precise pointing, its high-gain antenna could no longer face Earth. Its cameras would drift, its instruments would lose their targets. Communication would eventually stop. Every maneuver consumed a little more hydrazine. Every year brought the mission closer to an unavoidable decision. NASA faced a dilemma unlike any encountered earlier in the mission. Cassini itself had become a contamination risk. Scientists now believed Enceladus possessed a potentially habitable subsurface ocean. Titan also remained a compelling target in the search for prebiotic chemistry. If Cassini eventually lost control naturally, orbital calculations showed there was a small, but real, chance it could someday crash into one of these moons. The spacecraft had been carefully sterilized before launch, but absolute sterility is impossible. Tiny Earth microbes, protected deep within the spacecraft's structure, might theoretically survive. Even an incredibly small risk became unacceptable. After discovering worlds that might support life, NASA could not allow one of its own spacecraft to contaminate them. The mission that had revealed these extraordinary environments now had to protect them. Planetary protection policies became the deciding factor. Rather than allowing Cassini to drift unpredictably for decades or centuries, mission planners chose a controlled ending. The spacecraft would be deliberately destroyed inside Saturn. No debris would remain, no future contamination could occur. It was an emotional decision. Many engineers had spent most of their careers working on Cassini. Some had joined the project in the early 1980s. They had watched the spacecraft launch, travel across the solar system, transform our understanding of Saturn. Now they would command it toward destruction, intentionally. But if Cassini had to die, scientists wanted to learn as much as possible before the end. That idea evolved into one of the boldest mission extensions ever attempted. It became known as the Grand Finale. Beginning in April 2017, Cassini started performing a series of daring orbital dives between Saturn and its innermost rings. No spacecraft had ever attempted this before. There was a reason. Nobody knew whether the gap was truly safe. The region between the rings and Saturn spans roughly 2,400 kilometers. From a distance, that sounds enormous. In orbital mechanics, it is extraordinarily tight, even worse. Scientists did not know how much dust existed there. Traveling at nearly 12,000 kilometers per hour, even a particle only a few millimeters across could severely damage the spacecraft. Mission planners had incomplete information. There were no previous measurements. Cassini itself would become the experiment. On April 26, 2017, Cassini executed its first plunge through the gap. Mission control waited. Radio signals disappeared temporarily as expected. Then, the spacecraft emerged, completely intact. The anticipated barrage of dust never arrived. The region proved far cleaner than many researchers had feared. It was another mystery. Why was the space between the rings and Saturn so empty? What processes had cleared it? The answers remain an active area of research. Over the following months, Cassini repeated the maneuver again and again. 22 dives in total. Each pass collected measurements impossible to obtain any other way. The spacecraft measured Saturn's gravitational field with unprecedented precision. It sampled the planet's upper atmosphere. It mapped magnetic fields closer than ever before. It investigated ring mass. It examined plasma environments. Every orbit pushed the spacecraft deeper into unexplored territory. Every pass reduced the margin for error. There would be no rescue mission, no backup spacecraft. One mistake would end everything. The data transformed scientists' understanding of Saturn itself. For decades, researchers had debated the total mass of the rings. Were they ancient remnants from the birth of the solar system, or relatively young structures formed by the destruction of an icy moon? Cassini's close gravitational measurements suggested the rings were probably much lighter than many previous estimates. Combined with evidence that ring material gradually falls into Saturn, a process now called ring rain, the findings implied the rings may not survive forever. Instead of permanent features, they appear temporary on cosmic timescales. Current estimates suggest Saturn could lose much of its spectacular ring system over the next 100 million to 300 million years. That sounds unimaginably long. Astronomically, it is surprisingly brief. If intelligent civilizations had emerged earlier, or much later, they might never have seen Saturn wearing its iconic rings at all. The grand finale also produced one of the mission's biggest surprises. Saturn's magnetic field appeared almost perfectly aligned with its rotational axis. Too perfect. Most planetary dynamos generate at least a slight tilt. Earth's magnetic field certainly does. Jupiter's does as well. Saturn's seemed almost mathematically symmetrical. That posed a serious problem. Scientists use magnetic field variations to measure how fast giant planets rotate internally. If the field is perfectly aligned, that method breaks down. Even today, researchers continue debating Saturn's true internal rotation period. Cassini answered one question, only to expose another. And then there was the atmosphere itself. Each increasingly close orbit allowed Cassini to taste the very edge of Saturn's gaseous envelope. Atoms, molecules, charged particles. Unexpected interactions between the rings and the atmosphere began appearing in the data. Material from the rings was literally falling into the planet at enormous rates. Scientists estimated that thousands of kilograms of icy material were raining into Saturn every second. The rings were not isolated structures. They were slowly feeding the planet beneath them. A process nobody fully appreciated before Cassini's final mission. With every orbit, one reality became clearer. The spacecraft was approaching its final day. Mission planners had calculated the ending years in advance. Every maneuver, every transmission, every observation, there would be one last engine burn, one final trajectory adjustment, and then there would be no turning back. The countdown had already begun. By early September 2017, every command sent to Cassini had become irreversible. There would be no rescue maneuver, no emergency escape, no second chance. Mission controllers were no longer trying to keep the spacecraft alive. They were preparing it to die as productively as possible. Everything now depended on a carefully calculated sequence measured down to the second. On September 11, 2017, Cassini made its final close flyby of Titan. It wasn't simply a farewell. Titan's gravity acted as the spacecraft's last steering mechanism. Mission planners sometimes called it the goodbye kiss. Passing just over 119,000 kilometers from Titan's surface, Cassini borrowed exactly the amount of gravitational energy required to change its orbit forever. After that encounter, the spacecraft was no longer orbiting Saturn in any meaningful sense. It was falling. Its new trajectory intersected Saturn's upper atmosphere. Nothing could stop it. The laws of orbital mechanics had already decided the ending. For the next 4 days, Cassini continued transmitting scientific observations. Its cameras captured some of the last detailed images of Saturn's cloud tops. Its instruments monitored charged particles surrounding the planet. Its radio system remained locked on Earth with astonishing precision. Even knowing the mission was ending, engineers refused to waste a single minute. Every byte of information still mattered. Then came the final morning. September 15, 2017. Long before sunrise in California, scientists gathered inside Mission Control at NASA's Jet Propulsion Laboratory. Some had worked on Cassini for decades. Others had joined only during its later mission extensions. But everyone understood they were witnessing the end of one of humanity's greatest scientific expeditions. The room was unusually quiet, not because people had nothing to say, because every person there knew history was unfolding in real time. Meanwhile, nearly 1.5 billion kilometers away, Cassini continued exactly as programmed. There was no pilot, no artificial intelligence making decisions, only software written years earlier, executing instructions with extraordinary precision. The spacecraft rotated its large dish antenna directly toward Earth, not to receive commands. There was no time for that anymore. Instead, the antenna became something else, a shield. Its broad surface would absorb the first impacts from Saturn's increasingly dense atmosphere, protecting the scientific instruments mounted behind it for just a little longer. That simple decision bought valuable seconds of additional data, seconds that would become scientifically priceless. At first, nothing dramatic happened. Cassini skimmed through the extremely thin upper atmosphere. Individual atoms struck the spacecraft faster and faster. Hydrogen, helium, trace amounts of heavier elements. The impacts were microscopic, but at an entry speed of approximately 113,000 kilometers per hour, even isolated atoms carried enormous energy. Gradually, the atmosphere began pushing back. Tiny aerodynamic forces appeared. For the first time since launch, Cassini experienced something resembling flight, not controlled flight, resistance. The spacecraft's onboard thrusters immediately responded. They fired repeatedly, correcting its orientation, keeping the antenna locked on Earth, keeping the instruments pointed correctly, keeping the data flowing. Every thruster pulse consumed precious hydrazine, but there was no reason to conserve fuel anymore. This was exactly what it had been saved for. The deeper Cassini descended, the harder the atmosphere pushed. The spacecraft's guidance system fought continuously against increasing drag. Thrusters fired almost constantly. For a brief period, they succeeded. Cassini remained stable. It continued transmitting measurements directly from Saturn's upper atmosphere, data that had never been collected before by any spacecraft. Scientists were effectively sampling the edge of a gas giant in real time, a place no probe had ever survived long enough to study. Among the most valuable measurements were direct readings of atmospheric density. For years, scientists had relied on theoretical models describing Saturn's upper atmosphere. Cassini was finally testing those models against reality. Some predictions proved remarkably accurate, others did not. The atmosphere behaved differently than expected. Density varied more than several models had predicted. Subtle differences in temperature and composition became apparent. These details might sound small, they weren't. Understanding atmospheric structure helps scientists interpret everything from planetary evolution to magnetic field interactions and climate systems on giant planets. Cassini was still making discoveries, seconds before its destruction. Then came the critical moment. Atmospheric drag increased beyond what the spacecraft's thrusters could overcome. The onboard computer detected the growing instability and automatically commanded maximum correction. Every remaining thruster fired at full capability. For several seconds, the spacecraft fought back. It almost seemed alive, holding position, maintaining communication, refusing to surrender. But physics always wins. Eventually, the atmosphere generated more torque than the thrusters could counteract. Cassini slowly began rotating away from Earth. Only a fraction of a degree at first, then more. Its radio beam started drifting. The signal reaching NASA's Deep Space Network weakened almost immediately. Engineers watching real-time telemetry understood exactly what was happening. No one needed an announcement. The numbers told the story. At approximately 10:55 UTC, the signal vanished completely. There was no dramatic final message, no farewell transmission, no warning. Simply silence. Exactly as expected. Because of the immense distance between Saturn and Earth, Cassini had actually stopped functioning about 83 minutes earlier. Mission Control was not witnessing the spacecraft's death. They were witnessing news of a death that had already happened. Inside Saturn's atmosphere, events unfolded rapidly. Without stable orientation, aerodynamic forces increased dramatically. The spacecraft began tumbling. Temperatures soared. Friction converted tremendous kinetic energy into heat. External structures failed. Electrical systems stopped operating. The high-gain antenna melted. Fuel tanks ruptured. Scientific instruments disintegrated. Within moments, the entire spacecraft broke apart. Most components vaporized completely. Tiny traces of Cassini mixed forever into Saturn's atmosphere. No wreckage remained, only atoms. Mission Control erupted into applause, then tears. Some engineers hugged, others simply stared at their screens. The mission had ended exactly as planned. That success carried an emotional weight difficult to describe. For nearly 20 years, Cassini had been more than hardware. It had become a companion, a daily responsibility, a shared purpose across multiple generations of scientists and engineers. Now it was gone. Yet almost immediately, researchers turned their attention back to the data. Because the final transmission contained something remarkable. Cassini had survived longer inside Saturn's atmosphere than many simulations predicted. Its thrusters had maintained stability under increasingly hostile conditions. That extra survival time extended the scientific dataset beyond original expectations. It provided additional atmospheric measurements from lower altitudes than engineers initially believed possible. Those extra seconds mattered a great deal. But another puzzle quietly emerged from the mission's closing analysis. As scientists examined the final grand finale measurements over the following months, they realized Saturn's magnetic field remained extraordinarily symmetrical. In fact, even closer observations failed to reveal the expected asymmetry. The mystery became deeper, not simpler. According to long-established theories of planetary dynamos, giant planets should generate magnetic fields with at least slight irregularities. Saturn stubbornly refused. Its magnetic field appeared aligned with its rotation to an accuracy of less than a fraction of a degree. That created a fundamental scientific problem. If existing models were correct, Saturn shouldn't behave this way. If Saturn's observations were correct, some models might need revision. Another mystery involved the planet's interior. Cassini's precise gravity measurements suggested Saturn's core might not be a compact, solid object after all. Instead, researchers proposed something unexpected, a fuzzy core. Rather than a sharply defined center, Saturn may contain a gradual mixture of rock, ice, metallic hydrogen, and fluid extending across nearly 60% of the planet's diameter. If confirmed, this challenges traditional ideas about how giant planets form. Instead of neat internal layers, the interior may resemble a vast transitional zone where materials blend together over enormous distances. Again, Cassini answered one question by creating another. Even Saturn's famous rings refused to give scientists a simple conclusion. The grand finale revealed that ring particles continuously interact with the planet's atmosphere, magnetic environment, and plasma systems. The rings are not isolated ornaments. They are active participants in Saturn's evolution. Material falls inward. Electrical interactions occur constantly. Tiny particles migrate over time. The entire system changes, slowly, but continuously. Saturn is not frozen in time. It is still evolving, and Cassini proved it. By the end of 2017, researchers around the world had only begun analyzing the enormous archive Cassini left behind. Thousands of scientific studies would follow. Some questions found answers. Others became even more mysterious. And one of the biggest mysteries centered on a simple idea. Why did Cassini's last measurements reveal a Saturn that seemed more complicated than decades of theory had predicted? The spacecraft was gone, but its investigation had only just begun.